Okay, so section 1 of unit 3 taught us how to convert between the number of moles of a substance and the number of particles. Section 2 taught us how to convert between the number of grams and the number of moles, and then the reverse process, moles back to grams. Section 3 is going to get into something called percent composition, and then we will start talking about empirical formulas. Okay, so percent composition problems. These are actually going to be very similar to problems from Unit 2 that were percent by mass problems that most of you did fairly well on. So remember, going back to Unit 2, an example of this would say something like 4.04 grams of hydrogen in a 36.04 gram sample of an unknown compound. What is the percent by mass of hydrogen? Well, that formula was the percent by mass is equal to the mass of the element divided by the mass of the compound times 100. So we would just plug in the numbers here of 4.04, the mass of the element hydrogen, divided by 36.04 grams, the mass of the compound, times 100. We got 11.2% hydrogen by mass. Well, percent composition problems are going to be just like this, but they will be in reverse, and they won't necessarily give you any of these numbers. Okay, so it's a percent composition problem of, what is the percent composition of hydrogen in methane, CH4, something like that. Okay, so the problem here might say something like, calculate the percent composition of hydrogen in methane, right? The one from the previous slide. Okay, the formula here for percent by mass was, right, before it was just the mass of the element divided by the mass of the compound times 100. But to find the percent by mass, okay, this formula now for percent composition, it's the mass of an element in 1 mole of the compound. Okay, we'll do plenty of practice, so if you're not sure what this means yet, that's okay. Divided by the molar mass of the compound times 100. Okay, so if I'm trying to find the mass of hydrogen in CH4 methane, well, if I'm given no information on this, none at all, of where to start, what you go for is the molar mass of these elements. So the molar mass of hydrogen, well, we've got 4 hydrogens in this compound, H4. So in order to find the percent composition of hydrogen, I'm going to first take the molar mass of hydrogen times 4. Well, from your periodic table, we see that the molar mass of a single hydrogen atom is 1.01. Oh, come on here. 1.01 grams per mole. Well, in this instance, I, in fact, have 4 of them. Okay, so that means that in methane, the mass of the hydrogen is really 4.04 grams per every 1 mole of it. Okay, the mass of carbon in 1 mole of CH4, well, there's only 1 atom of carbon, so we took the 12.01 grams per mole times 1 and got 12.01 grams per mole. That's the mass of a single carbon atom. If I'm trying to find the percent by mass, then I got to plug in, depends on what I'm looking for. I'm looking for, in this instance, hydrogen. So the percent by mass, the mass of the element in 1 mole of the compound times 100. Okay, so the percent hydrogen by mass, well, we're going to plug in hydrogen, the mass of 1 mole of hydrogen in the compound divided by the molar mass of the compound times 100. Well, the percent hydrogen by mass, percent composition of it, 1 mole of methane has 4.04 grams per mole of hydrogen. Again, that number right there, this was coming from the 1.01 grams per mole. Again, always include units, don't forget to do that, times 4. That's where that's coming from, because there were 4 hydrogens. The bottom part, this number, this is the molar mass of the whole compound of CH4. That's the 12.01 plus the 4.04 added together times 100. And you get the percent by mass of hydrogen in methane is 25.2%. So these are really just like percent by mass problems. However, you're not given any of the original masses or anything like that. You look off of the periodic table. You get the molar masses. You multiply by however many you've got. In this instance, you had 4 hydrogens. There was only 1 carbon. And you plug that number in at the top there. Some people would make the mistake, common mistake here, of you'd put 1.01 grams per mole divided by 16.05 grams per mole. Well, that would be the case if you just had one hydrogen, but here you have four, so don't do that. That's not the correct way to solve this. Okay, so we are going to do several practice ones here. What has the larger percent by mass of sulfur? Okay, H2SO3 or H2S2O8. All right, so let's figure out the molar mass of each of these things here. Okay, so the whole compound, we're looking for sulfur. That's ultimately what we're looking for here. So let's find the molar mass of the whole compound. That's an easy one to do. Well, we'll call this one compound 1 right here. We have 2 times the molar mass of hydrogen from the periodic table, 1.01 grams per mole. You'll get familiar with these as we do them. Plus 1 sulfur, so element 16, that's going to be 32.06 grams per mole. Okay, plus oxygen's kind of a nice easy one. It's 3 times and we get 16.00 grams per mole. It's an easy one to remember, an easy one to work with. So this is for this first compound here, H2SO3. The molar mass of that whole thing is 2.02 plus 32.06 plus effectively 48, and that is 82.08 grams per mole. And if I want the percent composition of sulfur, well, this is all the mass due to sulfur right there. Okay, so if I want the percent sulfur, that's going to be 32.06 grams per mole divided by the molar mass of the whole compound, 82.08 grams per mole times 100. Okay, so for this first one, 32.06 divided by that number times 100, we get 39 point, and we'll just round this to the tenths place, 39.1% sulfur. Okay, let's do it for compound number 2. Molar mass of that one. Okay, once again, we got 2 hydrogens, so 2 times 1.01 grams per mole. Plus, this time we have 2 sulfurs, 2 times 32.06 grams per mole. Plus, then we've got 8, come on here, Apple Pencil, 8 times 16.00 grams per mole. We're going to need a calculator for this. 2.02 plus 2 times 32.06 plus 8 times 16. Okay, the whole thing weighs 194.14 grams per mole. Okay, the percent sulfur here, I got to take whatever that total is, and that's going to be the top. So 2 times 32.06, because I do have 2 sulfurs, not just one, I got 2 of them, 64.12 grams per mole, divided by the molar mass of the whole compound, 194.14 grams per mole, okay, times 100. All right, so divided by 194.14 times 100, this is 33.0% sulfur. So which one has the larger percent by mass of sulfur? Well, it is the first one. Even though there's 1 sulfur, it constitutes a larger percent. The nice thing about these is that these help identify compounds. So if you weren't sure if you had 2 unknown liquids and you weren't sure whether you had this one or this one, you could find the percent sulfur by mass of them. There's ways to do that to determine what your unknown was. Okay. So, an empirical formula problem. What is an empirical formula, first of all? Well, it's the formula of a compound with the smallest whole number mole ratio of the elements. Okay, so it's the smallest whole number ratio, smallest ratio. It might or might not be the actual formula of the compound. I'll give you an example here in a second of what that means. The actual compound might be some kind of multiple of the empirical formula. Okay, so you might do the work here, and we'll show you what this looks like in a moment. You might do the work and find out that the formula for the compound looks like HO. You have 1 hydrogen and 1 oxygen. Okay, that might be the actual formula, but it could be some kind of multiple of this. It could be times 2 or times 3 or times 4 of that. Okay, the actual formula of the compound will be H2O2, right? Hydrogen peroxide is what that would be. But the empirical formula of it is the simplest ratio. Well, this is 2 to 2, but the simplest version of that is 1 to 1. Okay, so that's why the empirical formula for hydrogen peroxide would look like this, even though the actual formula is double that. Okay, so you would be multiplying it times 2. But I'm going to show you how to find the empirical formula of a compound based on its percentages, its percent compositions. Okay, so a problem says to determine the empirical formula of a compound that is 72.7% oxygen by mass and 27.3% carbon by mass. So what to do in this situation? Well, step number 1 is to assume you have 100 grams of the compound. If you assume 100 grams of the compound, the percents very nicely turn immediately into masses. It's a very effective way of doing this, a very easy way of doing this. Okay, so that immediately turns into, like I just said, 72.7 grams of oxygen, right? Because 72.7% of 100 grams is that number right there, and 27.3 grams of carbon. Very easy way to do that. You want to then convert each amount in grams to a number in moles. Well, how do you do that? How do you convert grams to moles? You divide by the molar mass. Well, 72.7 grams of oxygen, okay, that's what we're starting with, divided by its molar mass is 16.00 grams per mole. That's going to give you 4.54 moles of oxygen. Do the same thing with carbon, but don't forget its molar mass is different, 27.3 grams. Converting to moles, you divide by its molar mass, 12.01. You get 2.27 moles of carbon. So step 3 is to convert the number of grams into moles. Grams to moles. Okay, that is step number 3, which really means divide by the molar mass. Okay. All right, step number 4. Now you want to find the mole ratios. Okay, step 4 is to find the mole ratios. Well, we've got 4.54 moles of oxygen to 2.27 moles of carbon. And I want to simplify this down, okay, because this is not an easy way to do it. So simplify by dividing each by the smallest number of moles present. Okay, so step 5, divide by the smallest number of moles present. Well, the smallest number of moles present in this is 2.27. If I divide them both by 2.27, this very nicely, very conveniently, 4.54 moles of oxygen divided by 2.27 gives you 2 moles of oxygen, and this is going to obviously give you 1. Okay, so you have 2 moles of oxygen for every 1 mole of carbon. My ratio of oxygen to carbon is 2 to 1. Therefore, the compound here is, well, we're going to rewrite it with carbon first, CO2, carbon dioxide. Very convenient, very easy way of figuring out the percent, finding the empirical formula of it using the percent composition, 72.7% oxygen and 27.3% carbon by mass. That compound is CO2. Okay, so we used a few steps to get us to that point. Okay, so we figured this one out, and from that, we figured out the formula. Step 6 was to use the simplest whole number ratio to figure out what the empirical formula actually is. Okay, so let's try one that's got a few more elements in it. Determine the empirical formula of caffeine if it is 49.5% carbon by mass, 5.2% hydrogen, 28.8% nitrogen, and 16.5% oxygen. So here we got 4 elements to deal with. We'll see how well this turns out. Now, remember, these are measurements, so it may not be a perfect answer. We'll see what we get. Okay, so step 1 was to assume 100 grams, exactly 100, right? So that way we don't have any sort of error there with significant figures. So I've got carbon, and that is 49.5 grams of it. Okay, and I want to convert that over into moles, so we'll divide by 12.01. That's the molar mass of carbon from your periodic table, grams per mole. So 49.5 divided by 12.01 with 3 significant figures, 4.12 moles of carbon. Now we need to do it to the other elements. Hydrogen, we got 5.2 grams of hydrogen divided by its molar mass, 1.01 grams per mole is equal to, so 5.2 divided by 1.01. It's going to be very close to 5.2, a little bit less. I'm going to use 3 significant figures here just to give us a better number to work with. 5.15 moles of hydrogen All right, and we'll go over to nitrogen. We've got 28.8 grams of it now, divided by its molar mass, 14.01. That's from your periodic table. That's where I'm pulling that number from. 28.8 divided by 14.01. It's going to be close to 2. And we've got 2.06 moles of nitrogen. And lastly here with oxygen, we've got 16.5 grams of it, divided by 16.00 grams per mole. Okay, that's going to be close to 1. 16.5 divided by 16, we have 1.03 moles of oxygen. Okay, so we've got all these converted into numbers of moles. My next step is to divide by whichever one is the least present. Well, that is 1.03 moles of oxygen. So we're going to divide all these numbers by 1.03. Okay, and I'm going to do this, I'll shift this up. There we go. And I'm going to do this underneath it. So 4.12 divided by 1.03. Okay, that's going to give us exactly 4. That's kind of convenient. So back to the carbon. This one divided by 1.03. This is now 4 moles of carbon. Okay. 5.15 divided by 1.03. This is exactly 5. Oops, divided by 1.03. This is now 5 moles of hydrogen. Hey, this is really working out kind of conveniently. 2.06 divided by 1.03. Well, you can probably do that one in your head. Now we've got a nice even 2 moles of nitrogen. And this, of course, divided by itself is just going to give you 1, that does not look like a 1 mole of oxygen. So now what's my formula? Well, my formula is C4, okay, right there. And then we're going to have H5. We're going to have N2. And then lastly just O, because there's only 1 oxygen. Okay. So let's try a couple of practice problems on your homework. So this is on page 5 and 6, your 3-3 worksheet. So we're going to try a couple of those. All right, so the first one in this homework, number 1, says to determine the percent composition in each of the following compounds. This one is looking for sulfur in H2SO4. The molar mass, we got to figure out the molar mass of the compound. That's what it's looking for here. So H2SO4, well, we got 2 times the molar mass of 1 hydrogen, plus we got 1 sulfur, so 32.06 grams per mole, plus 4 times, and then oxygen is 16.00 grams per mole. Okay, the molar mass here, 2.02 plus 32.06 plus 64, that is 98.08 grams per mole. Okay, if I want to figure out the sulfur, percent sulfur, all right, that's going to be equal to, here the sulfur's mass in total is 32.06. Divided by the molar mass of the compound, 98.08 grams per mole, okay, times 100 is equal to, it's 32.06 divided by that number, times 100 is 32 we'll round it to tenths place, 32.7% sulfur. Okay, so that's how you would do one like number 1. Let's look at one like number 3. I just want to make sure we do number 3 correctly because number 3 has multiples of that atom that it's looking for. It's looking for iron in Fe2O3. So iron in iron 3 oxide. Okay. Well, the molar mass of this whole thing, we got 2 irons. Each iron is 55.84 grams per mole, okay, plus 3 times oxygen is 16.00 grams per mole. Okay, the molar mass of this whole thing, 2 times 55.84 plus 3 times 16. Okay, the whole thing, it's kind of heavy here, 159.68 grams per mole. All right, well, when I'm doing the percent iron, okay, It is this whole thing, 2 times this number, 2 times 55.84. Okay, so the percent iron is 111.68 grams per mole, divided by the mass of the compound, 159.68 grams per mole, okay, times 100. All right, and that is going to be, let's see here, it is going to be 69.9, make sure those all look good, 69.9% iron. Okay, now let's take a look at one on page 6 and finish this off so that you can finish up the rest of them. So we'll look at number 11. It says to determine the empirical formula of the compound given its percent composition. Okay, so this one is 77.7% iron and 22.3% oxygen. So step number 1 is to assume 100 grams and convert those values into grams. So for iron, we have 77.7 grams of it. Okay. And for oxygen, we have 22.3 grams of it. I'm going to convert them both into moles. That's the next step. So divide this by the molar mass of a single iron, 55.84 grams per mole. Okay, so I've got 77.7 divided by 55.84. That is 1.39 moles of iron. And this one, divided by its molar mass of 16.00 grams per mole. Okay, so 22.3 divided by 16. Okay, that gives us 1.39 moles of oxygen. Well, in this instance, both of them have the exact same number. Remember, we're going to divide by whichever one is the least amount. Well, they're both the least amount. So we divide this one by 1.39, divide this one by 1.39. We end up with 1 mole of iron for every 1 mole of oxygen. My compound's formula is very simple here. It is just FeO. Okay, and that is your answer. So try your best with pages 5 and 6 now. Try to finish all of those.